Hello, welcome back to Math 332 Linear Algebra. We are going to look at sections 2.3 today, and sections 2.3 will involve further discussions of properties of determinants. In particular, we are going to look at a theorem, very important theorem, which states that matrix A is invertible if and only if the determinant of that matrix is not equal to 0. And that's one of the main reasons why we study determinants, because it can give us information on the invertibility of a matrix. And this is going to be a slightly long section, so we are going to split this into two parts presentations. And the first part of the presentations will go over the proof of that particular theorem. So this video is going to be a little bit more theoretical. So we don't just state the theorem and look at the example, but instead we'll go through the proof. And that's the reason why the things will be slightly more abstract and complicated and theoretical, but I'm pretty sure you'll be able to get through it fine. And in the second presentation, we are going to look at another applications for determinants, where we can actually use it to write down a formula for the matrix, the inverse of a matrix, if the matrix is invertible. And that particular method is called the adjoint methods, and it will complement the methods that we have seen before, which is we can actually find the inverse of a matrix by going through row reductions. But sometimes that is not a very good method, and adjoint methods will complement that. And finally, in the second part of the presentation, we'll also look at another application for determinants, where we can actually write down the solutions for linear systems by using determinants. And that is what we call the Cramer's rule. And that will conclude and all the stuff that we need to know in chapter 2. All right, so this is the first part of the presentation, and let's get right to it. All right, let's begin by looking at the objective for this section. So at the end of this video, you should know that the determinant of Ka is not K times the determinant of A, but instead is K to the power of n times determinant of A, where the n here is the number of row or the number of column for the square matrix, okay? And it is also very tempting for you to say that the determinant of A plus B is equal to determinant of A plus determinant of B, but actually that property is not true. So I want to point out here, because these are the stuff that students usually tend to make mistake. But one of the main things we want to talk about in this video is that even though we don't have this property, but we do have this property, which is that if your A, B are square matrices of the same size, then the determinant of the products of these two matrices is the products of the determinant. So this is true, and we were going to demonstrate why this is true. And this is one of the main things that we want to talk about in this video. And obviously, the last thing we want to talk about, which is the main, very, very important facts in this chapter, is that we have a way to characterize the invertibility of a matrix, which means that we have a way to say that when a matrix is invertible, and we can say that a matrix is invertible if and only if the determinant of that matrix is not equal to 0. So we are going to go through the proof and show you why this is true. So because of that, the video is going to be a little bit theoretical, but I'm pretty sure you can get through it pretty fine, okay? All right, so let's do a very quick review on some of the properties that we learned from the previous video, and this is the things that I mentioned just now. I would want to say that again, because this is some of the stuff that students tend to think that we can just take the K out, but it's not. You're going to take the K to the power of n out, okay? And another thing we want to review is that when you have a matrix that looks like this and you're looking for the determinant, so you're looking for a determinant of a matrix that looks like this, we can look at this row here and we can do a cofactor expansions along this row. And this is the cofactor expansion along this row. You can distribute and regroup and you get something that looks like this. And this is going to be the determinants for this particular matrix. And this is going to be a determinant for this particular matrix. So what we do have is that determinant for a matrix is like that. You can do split it into two like this, and we used it before in the previous video. But that does not mean the determinant of A plus B is equal to the determinant A plus determinant of B. So remember, this is not an example to illustrate that this is true. So you can think of an example. You can give an example to show that this is not true. You can come up with a very simple example that shows that this matrices does not enjoy this property. So why don't you think about try to come up with a 2 by 2 matrix A, another 2 by 2 matrix B. Let's start from something small, right? When you want to give an example, we can give an example. Don't think about too complicated examples. So let's start with an easy example. So let's say your matrix A is of size 2 by 2. Your matrix B is of size 2 by 2. Can you come up with an example where this property does not hold? Okay. All right, I will give you a moment to think about the problems, and you can pause the video, and when you are ready, you can restart the video, and I will be here and show you what I got. See you very soon. All right, welcome back. I'm pretty sure you have an example with you. So there are definitely infinitely many different examples. So I'm going to show you mine, and you can also verify that whether or not your example is correct. So I am thinking of a matrix A that looks like this. All right, so this is my matrix A, and the determinant for this matrix is obviously 0. You can just do a very simple computations, or you can see that they will have a row of 0. So from the previous video, we know that having a row of 0 will definitely give you a determinant 0, because you can do a cofactor expansion along this row, and obviously the answer is 0. So I'm going to give my matrix B in this form. So I'm going to write my matrix B in this form. So this is my matrix B, and this is determinants of this matrix is also again 0. So this is my matrix A, and this is my matrix B, and you can see if I add it up, A plus B, so I can add this two matrix. This is 1, 0, 0, 0 plus 0. Oh, I want to change this to this, sorry. Okay, so this is going to be 0, 0, 1. So what I get is an identity matrix. So the identity matrix is my A plus B. So my determinants of A plus B, okay, is the determinant of this identity matrix. And as you know, the determinant of the identity matrix is 1. All right, so this relationship does not hold for this particular example, right? So my determinant of A plus B is 1, but then, okay, my determinant of A is 0, my determinant of B is 0. So you can see that this property does not hold. So we do not have determinant of A plus B equals to the determinant plus determinant of B, and this is one such example that can illustrate that, okay? All right, so even though we don't have this kind of property, but we do have this property though. This is a very surprising because usually the addition is the easier one. The multiplication is slightly more complicated. So if you have a property that does not hold for additions, you would think that this kind of property will be too good to be true. But the answer is no, actually this is true. So if you have two matrices of the same size, they are both n by n square matrix. Okay, so they are both n by n square matrices. The product of the determinant of the product, that's how we say it, the determinant of the product of the two matrices is actually equals to the product of the determinant, right? So determinant of the product is actually the product of the determinant. So this is actually a theorem, and we will want to prove it, okay? So we will want to prove it. And how do we actually prove a theorem like this? So again, we're going to introduce a lemma. So you have seen lemma before. So lemma is technically, it is a theorem. It's just that a theorem that is not that big a deal. And we usually use it to solve or to prove something that is bigger. So it's kind of like a stepping stone, something that can help us. So it's still technically a theorem, but we call it a different name. So it's called a lemma, so that it can help us to solve bigger problems, to prove a bigger theorem. And the bigger theorem we want to prove is this one. So this is kind of like a small steps before we get to that. And so we're not going to prove that the determinant of AB, okay, is equals to the determinant of A times determinant of B. Instead, we're going to show that we have something that's similar to this, but we are not looking at any general matrix A, but instead we are going to claim that this property hold, okay, if your matrix here, this particular matrix here, is an elementary matrix. Okay, so we're going to start from that. So we are not going to do any general matrix A, but we are going to do matrix E. This matrix E is our elementary matrix. So we're going to claim that the determinant of the product of these two matrices, one of them is the elementary matrix, can be written like this, okay? So before we do this, let me just remind you that technically speaking, we have only 3 types of elementary matrices. So remember the definition of elementary matrix. So elementary matrix is obtained by doing a single row operation from the identity matrix. So you can do, for example, interchanging the I and the J row. So you get to these elementary matrix with a notations that is like this, right? So we know that the determinant, okay, with the determinant of this matrix, okay, determinant of this elementary matrix is going to be equals to -1, because interchanging 2 row of a matrix will give you a negative, right? And this is determinant here is 1, so the answer is -1. We know that. And if you do elementary row operation on the identity matrix by taking, let's say, row I and multiply row I by k, and remember though, when we do elementary matrix operations, the elementary row operations, this k here cannot be a 0 number, okay? It can't be 0. You would never, when you do row operation, you will never multiply a row by 0, because then the row operation is not legit. You completely destroy that row that might contain information. So this particular k here is never 0. And then you get to this elementary matrix, which we denote by Ri, and then change it to k times Ri. And it's not difficult to see that this determinant is k. And then finally, we also have another row operations and elementary row operations, that is taking the Ri and change it by taking Ri plus k times Rj. Again, this k here is taken to be non-zero, and you get this elementary matrix with the notations that looks like this. And we also know that the determinant for this matrix is actually just 1, because the determinant for this matrix and the determinant of this matrix will be the same. And all these are properties that we have discussed before in the previous video. So first note that the determinant of elementary matrices, they are all non-zero. They're either -1, or they are 1, or they are any real numbers that is not equal to 0. So this will be information that we'll need pretty soon. So just bear in mind that the determinants of the elementary matrices are going to be non-zero. None of them is 0, okay? If you actually do a legit row operation, these are kind of legit row operations, elementary row operations, then the determinant of those elementary matrices is never equal to 0. All right. So we are not going to prove this lemma here. Instead, we are going to ask you to do it in your homework. So this is one of the homework problems. And actually, this technically is not really proof. The general proof will be a little bit more complicated, because your matrix A will be of size n by n and all that. So notation-wise, it's going to be a mess. But the idea is similar. So we are going to just show it by example, so to speak. So you are given, so this is one of the example where you are given an elementary matrix. This is an elementary matrix, as you can see. Okay, you can think about how do we get this elementary matrix from I. All right, so you can get it from one row operations and do it, perform it on the identity matrix. So this is an elementary matrix. So you have a matrix B. Let's do it on this matrix of size 3 by 3. So you are asked to compute what happened when you multiply this matrix B with this matrix E. This is something that you know how to do from before. And then I want you to find the determinant of EB. Okay, so I want you to compute. Don't multiply everything out, because the computation is going to be a mess. So I'm actually asked you to do a cofactor expansions along a particular row. And then I want you to compute the determinant of E. That's easy. And then I want you to show that in this case, the determinant of EB is actually the determinant of E times determinant of B. So the answers look something like this. So if you are given E like this, okay, obviously that's how you get the E. It's an elementary matrix. The EB will be this. We know that from before. And if you compute the determinant of EB by doing row expansions, cofactor expansions along this particular row, you will get that. Now, the key thing is not to multiply everything out. Then you will be in trouble. You'll be whole bunch of algebra soup, and you can't get out of that soup. In fact, you will drown in that soup. So you just do a cofactor expansions along this row. Just do a cofactor expansion along this row. So that's in the hints of the problem. You could do a row cofactor expansion along this row. So you get all this. This is nothing but doing a cofactor expansions. and then you can multiply, and distribute. So you can break this into two different parts. You can break the computation right here into these two different parts. And then if you look at these two different parts separately, so if you look at these two different parts separately, you will see that this part right here is actually this determinant, and this part right here is actually this determinant. So you don't have to multiply it out to see that. Okay, you just have to get very comfortable with the cofactor expansions. So you will see that this is actually this, and this is actually this. Okay, so this is obviously determinant of B, and this again utilizes the property that we know from the previous video. This is 0. Why is that so? Because we have this row right here and this row right here, they're identical. So we know from last time, if you have a matrix with two identical rows, or the rows are multiple of each other, then you will know that this is determinant 0. So determinant of EB is actually equals to determinant of B in this case, but your determinant of E is 1, right? So your determinant of EB is equal to determinant of B, but your determinant of E is 1. So you can write determinant of EB equals to 1 times this, but 1 is your determinant of E. So if you drop the detail and just look at this, you see that we actually have that equality hold, not for all E in this homework problem, but for this E, okay, for this E. And we also have some other different E that you need to do it in the homeworks to verify and get an idea how the proof will goes. But this is not a proof in general, but by doing this exercise, you will see that in general, it will work like this. So we don't go through all the possible elementary matrices. That will be, if you want to really write this proof perfectly and in full generality, it's just going to be a lot of writing. It doesn't really show a lot of insights. The insights is actually shown here. You can see that all of them will involve computation that kind of looks like that. And by doing that, I believe you will understand why that lemma is true, okay? So the lemma says that, well, if you have an elementary matrix, okay, if you have elementary matrix, then the determinant of EB will be equals to determinant of E times determinant of B. Have we proved this theorem yet? No, we haven't proved this theorem yet, okay? This is something that we aspire to, but we haven't got it yet. But we got some part of it, okay? We got that if the A here is E, if the A here is an elementary matrices, then that's fine. But this is what we aspire to, but we haven't got to that point yet, okay? So let's move on, okay? So remember what we aspire to, and let's move on. So before we prove that theorem, we actually wanted to do this first, okay? So remember, this is the key thing, the reason why we want to study determinants, because it can give us a criteria to show when a matrix is invertible. So this theorem, which is in the book labeled as 2.3.3, it says that a square matrix A of size n by n, all right, is invertible if and only if the determinant of A is not equal to 0. So it says that A, so it is two parts, right? This theorem is if and only if. So it says that if A is invertible, right, then, all right, determinant of A is not equal to 0. That's the first part, okay, because it's if and only if. So the second part is if determinant of A is not equal to 0, then, right, A is invertible. So this is two parts. So I keep saying that determinants give us a complete characterizations of its invertibility. When I say complete characterization, that means that if A is invertible, then the determinant is not equal to 0. The determinant is not equal to 0, then A is invertible. So this is a very nice theorem that it goes both ways. A lot of theorems only go one way. So for those of you who dated before, you know that most of the time your love is just one way, right? So you say, I love you, but the person say, I'm sorry, I'm getting a restraining order, right? So it's very rare that you get the two-direction love. It says, I love you, and the next person say, I love you too. That's rarely happened. So in math, it's also the same thing. It rarely happens you have a theorem that go both way, if and only if. And when you have that, oh my God, that's good, right? So this is why I keep saying that determinant can give you a complete characterization of the invertibility of the matrix. It goes both ways. So another way of stating this theorem is this, because if you go both way, you can take the contrapositive. We haven't talked about that. We talk about that in the homework, but just trust me on this, that this is logically equivalent to this statements right here. So this statement says that if your matrix is not invertible, then your determinant of A will be 0. Or if your determinant of A is equal to 0, then your matrix is not invertible. So these two are logically equivalent, okay? They are logically equivalent, okay? Matrix A invertible if and only if determinant not equal to 0. Or matrix A not invertible, then the determinant of A is not equal to 0, which is equal to 0, okay? So we are going to set up to prove this particular versions of the theorem. So as I said, it goes 2 parts. So now we're going to do the proof. Okay, let's get ready. So this part right here means that we're going this way. That is, we are going to say that if A is invertible, then we want to show that the determinant of A is not equal to 0. So the first line of the statement here is a statement of what we want to achieve. Sometimes it's good to write this thing down so to indicate what you want to do. All right, so we want to do in this part is to assume that A is invertible. So suppose we know A is invertible, and what is your job? Your job is to show that the determinant of A is not equal to 0. So let's go ahead. So A invertible from the previous videos, previous section on invertibility of a matrix, we know that you can row reduce A all the way to I, remember? Okay, so we last time did talk about something that's like this. If you put an augmented matrix, if you row reduces to I, you get this. This is going to be inverse of the matrix. So in particular, you can see that if A is invertible, you can row reduces it to I. That's something that we know from last time. So if your matrix A is invertible, from hypothesis, from our assumption, so there exist elementary matrices such that if you perform these elementary matrices, multiply all this thing on the left-hand side of A, you get I. This is again from the previous video. This is the same as saying that your A can be row reduced all the way to I. Okay, all right. So now let's take the determinant of this part. Okay, let's take the determinant of this part and take the determinant of this part. So this is why you see we have this and we have this. And obviously the determinant of the identity matrix is 1, so we're not going to write that. We're just going to write 1, 1, 1, 1, 1. And now, okay, and now remember the lemma, right? Which we kind of justified the lemma, justified, not fully proof. So we know that the determinant of E times B is going to be the determinant of E times determinant of B if your E is an elementary matrix. Okay, so let's bracket it this way. You can see I bracket it this way. So this EK here is definitely elementary matrix, but all this thing here is not an elementary matrix. This is some other matrix, some other matrices that we call B. So you see that E is definitely EK is definitely elementary matrix, but this is not. But so we kind of like look at that as our B. So we split them. So you have this and then you have this. So we are kind of like getting this and this by doing that. But then we repeat the process. Okay, we look at EK minus 1 and the rest of it, this one is called B. And we can split that again to this. And if you see, we can keep splitting. At the very last step, you will have something that's like this, right? And then this is, again, an elementary matrix. This is not, but we know that this can be split into something that looks like this. So we manage to split, and now you can see why we use that. We need that lemma. So we managed to split all the way to here. So this is the consequence of having A invertible. Okay, so now you see A is invertible, give us this. All right, so now another thing that we just mentioned, that the determinant of the elementary matrices are non-zero. These are all non-zero. So these are non-zero. These are all non-zero. So non-zero, non-zero, everything is non-zero. Multiply all together. This is non-zero. So this is 1. So now you have a non-zero numbers, multiply determinant of A and get a non-zero number. So obviously this here cannot be 0. So that's how we see that the conclusions is that the determinant of A must not be 0. So that's the conclusions. See it? So the key things in this proof is to utilize that A invertible means that A can be row reduced to I. Therefore, you introduce all those elementary matrices all the way here, and then write down the determinant, try to compute it, do the lemma, get to all the way to this line, Notice that the determinants of all this elementary matrices is not equal to 0, and we have to get to 1. So your determinant of A has no choice, but has to be non-zero. So now we know determinant of A is if A is invertible, determinant of A is not 0. Okay, so this part here, okay, well, I have to utilize a little bit more thought, but the idea is, okay, so this direction means that we are going to use this as our hypothesis now. So we are assuming the determinant of A is not equal to 0, and we want to show that A is invertible. Okay, so now we are assuming, okay, assuming the determinant of A is not equal to 0, and we want to show that A is invertible. So how do we do that? So now we assume that we take A and row reduces it to an RREF matrix. So we row reduces to an RREF matrix. We don't know that this is an identity matrix or not. If this is the identity matrix, then A is invertible, right? If your A can row reduces to an identity matrix, then that identity matrix here will imply that this is invertible. So we don't know that. We want to show it's invertible. So the only thing we can say is that, hey, let's assume that we can row reduce our matrix A to an REF matrix, and use this hypothesis to force that your R has to be I. So you want to force this, okay? You want to force your your R here has to be I. So in the beginning of the proof, we can say that, okay? In the beginning of the proof, okay, we just say that, hey, let's row reduce, because we can always row reduce a matrix, right, to its REF form. So again, row reduces a matrix to REF form is equivalent to multiplying all those elementary matrices. And now again, we use this lemma. So let's compute. So let's look at this equation here, and let's compute the determinant. So determinant of this is determinant of this. I'm skipping a lot of steps here because now you know that you can use the lemma and split all this thing here to determinant of this, multiply determinant of this, all the way to this, okay? All right, so I'm actually skipping a lot of steps. That kind of looks like this. Okay, so now you know by using the lemma, we can get all the way to this step. All right, so what do we know? So we know that the determinant of A is not equal to 0. So this determinant A is not equal to 0. That's the hypothesis. And obviously, again, all this determinant of the elementary matrices is also not equal to 0. So what we can say is that we don't know what that R is, but we know that this RREF matrix has determinant that is not equals to 0. Now, REF matrix is a very special matrix, okay? So REF matrix is a very special matrix. So this theorem, 1.4.3 on page 43 on your textbooks, says that if you have a REF matrix, okay, and so for example, if you have something that looks like this, okay, this is a REF matrix, then you will have a row of 0. The determinant of this matrix, this REF matrix, will be 0. And what they are saying is that if you don't have that, right, if you have another 1 right here, then because it's REF, this thing here has to be 0, this thing here has to be 0. So what it says, which is kind of easy to think about, you just have to think about, is that if you have a REF matrix with determinant not equal to 0, your REF matrix actually do not have a choice. Your REF matrix here, which have determinant not equal to 0, doesn't really have a choice. It really have to be I. That's what it said. So think about it, or you can look at the proof of this theorem that says that if your RREF matrix, not any matrices, okay, not any matrices, but your RREF matrix, if it does not have determinant that's 0, like the determinant is not equal to 0, this R here really have no choice but to be identity matrix. Bear in mind that this R here is also square matrix, okay? This is a square n by n matrix. Square n by n matrix, RREF, determinant not equal to 0, that R has to be I. Which means, okay, so let's get rid of all this. Okay, let's get rid of all this. What does it mean? Okay, it means that, okay, you take A, row reduces to an RREF matrix if the determinant, so this is the hypothesis, if the determinant of A is not equal to 0, then your R here is I. Which means if your determinant of A is not equal to 0, you can row reduces A to I, which means your A is invertible. So that proof this direction. Determinant of A not equal to 0, your A is invertible. We have shown that, and that's complete the proof. And that's complete the proof of this theorem. And this is now, you can see why the determinant of A is so useful. the determinant of A is so useful. It gives you a complete characterizations, give you all the information you need to know on when a matrix is invertible. Okay, so that's pretty nice. Okay, so now we have that. Okay, so now we have that. Okay, we are ready to prove this theorem, which is theorem 2.3.4, which is the main thing we want to prove. If A and B are square matrices of the same size, you can write the determinant of the product and the products of the determinant. Now, A here is no longer assumes to be elementary matrices, but any matrices. Okay, so how do we prove that? So again, take a deep breath. This is the second proof you're going to see. So this video has 2 theorems and 2 proofs. So let's break it into cases. So the case 1 here is assumes that something that we know from the homework. So in the homework, we didn't prove this using definitions, using determinants. Okay, so this is important because we don't want our arguments to run in loops. So in the homework, we actually prove the statements without using determinants at all. We just use the definitions. So the homework says that if your A is not invertible, if you have a matrix A is not invertible, these are all square matrices, then your AB is also not invertible. So A not invertible, not invertible. This is a homework. A not invertible, invertible. Then, right? So this is if A not invertible, then AB also not invertible. So we prove it using the definition in the homework. We are not using determinant at all. Okay, right. So now the case 1 is to assume that A is not invertible. Now, from the previous theorem that we already established, theorem is 2.3.3. So 2.3.3, we already established everything we need to know about invertibility, right? So we know that if A is not invertible, then the determinant of A is 0. But AB is also not invertible, right? So the determinant of AB is also 0. So A not invertible, meaning that this is 0. AB is also not invertible, which means this is also 0. So you can see that this equality actually hold. The left-hand side will be 0, the right-hand side will be 0. We don't care about determinant of B because this one here is already 0. 0 times whatever is 0. So this equality hold for case 1. So case 1 assume A not invertible. If your A is not invertible, we do have this equality. We have a trivial equality that both sides equal to 0, but nonetheless, we do have determinant of AB equals to this. All right, so first case is done. Okay, we have to get this over with. So first case is done. Okay, so now we are going to look at what happens if A is invertible, because you are breaking things into 2 cases, right? So the 2 cases add up will have to be everything, right? So so case 1 and case 2, okay, add it up will be all the possible cases that you can think of. So case 1 is A not invertible, right? Not invertible, and we have that result, right? And so case 2 will be A invertible. So we have to show that too. So A invertible. So do we have that? Okay. So do we have that? So let's do this. If A is invertible, again, we can row reduce A all the way to I, which means there's all these elementary matrices such that your A can be written like this. This just means that A can be row reduced all the way to the identity matrix. Now, determinant of AB, right, will be determinant of all this because this is A, right? This is A and that's B, right? So determinant of AB will be this. And again, this part right here, using the lemma, we know they can split all this thing up to here, okay? All right, so this is because of the lemma. So the lemma is actually critical, okay? It's actually critical. So determinant of AB is equal to this. And right here, you split everything out and multiply that. So now you look at this. This is, again, determinant of A. So determinant of AB is split into all this times determinant of B, and this is actually determinant of A times determinant of B. So again, if you suppress all the detail and just look at this, you will see that determinant of AB is equal to the determinant of A times determinant of B, in this case where A is assumed to be invertible. So all both cases here is true, okay? So all those both cases here is true. And we see that, hey, we do have this property for all AB square matrices. All right, so the key is to first do it for the elementary matrices, and then we uses that to show that, in fact, this property does hold for all type of matrices. Doesn't really have to be elementary matrices. So the final thing is that this is the homework problems where we never uses the concept of determinants. Okay, so we use the definitions. So we say is that, hey, suppose you have AB square matrices of the same size. A is not invertible, will implies AB not invertible. So we did that in the homework using nothing but the definitions and special proof techniques, but we use nothing but definitions. But suppose we don't want to use definition, we want to use the new thing that we just learned, which is determinant. We can also do it this way, okay? So we want to show, okay, so this is another alternative solution. This is alternative solution for this statement. So AB square matrices of the same size, A not invertible. So A not invertible, show that AB not invertible. So show that AB not invertible. So let's compute the determinant of AB, because if you can show this, then you know they are not invertible. So let's do that because we have all that theorem now. So first thing we do is we can apply the theorem that we just learned. We can split this into two. Very nice. We can do that. And the hypothesis is that A not invertible. So we also use the previous theorem, which is 2.3.3, that says that if it is not invertible, this is 0. So hypothesis A not invertible give us this 0. So this multiplied this will be 0. So again, the determinant equal to 0 will implies AB not invertible. Okay, so this is another thing, very, very short. If you compare the solutions to the solutions in your homework, this is actually way shorter because we are using powerful tools, right? So this shows that determinant of AB, look at this. If you get rid of all this detail, you see that determinant of AB under this hypothesis, determinant of AB is 0. So that means AB is not invertible. AB is not invertible if A is not invertible, okay? All right, so this is using very powerful tools, okay? Very powerful tools to help us do that. All right, so there's another question I want to ask you, which is this one, and then we'll conclude this section. So the question here is that suppose your A is a n by n square matrix, and it is invertible, so we can assume that that's a hypothesis, it's invertible. So let's assume that the determinant of A is alpha, and we also know from the theorem that alpha here is not equal to 0. So the question is, if you know the determinant of A is alpha, A is invertible, what is the determinant of A inverse? So A inverse, what's the determinant, okay? What's the determinant? All right, why don't you pause the video, take your time and work on that, and I will come back and show you what I have. All right, welcome back. Okay, let me show you the solutions, okay? So now the hypothesis is that A is invertible. So A multiply A inverse will equals to the identity matrix. That's the definitions of invertibility of the matrix. All right, so now let's take the determinant of this matrix, AA inverse, and that is the determinant of I. And determinant of I, the determinant of identity matrix is 1, that's obvious. Now, this part right here is the determinant of two matrix, a product of two matrices. So by the theorem we just proved, we can split them into determinant of A and determinant of A inverse. Okay, so this is a theorem we just proved. Now make use of it, you will see something that's like that. So what is determinants of A inverse? Okay, so this one right here, this is what we call alpha. We know that A is invertible, so this alpha here, this number here is not 0. So it's not 0, we can divide. If it is 0, we cannot divide by 0, so we can divide. So this is determinant of A, right? So you can see that the determinant of A inverse is 1 over determinant of A. So determinant of A inverse, according to our questions, that determinant is called alpha, so we can write it like this. If you don't like to write it like this, you can continue to write it like this. If you don't want to write it like this, you can also write it like this. Hopefully you don't get yourself confused. I really hope you don't get yourself confused, but this is this, okay? High school algebra, or what we call preschool algebra. This is also can be written like this. So the determinant of A inverse is this, okay? I hope you get the correct answers. All right, this concludes our discussion on the first part of sections 2.3, where, as you can see, the determinant is actually pretty useful. We managed to reduce the entire matrix to one number, and that number gives us a criteria to determine when a matrix is invertible. So in the next video, we are going to explore some of the properties for determinants. In particular, we are going to look at how we can use the idea of determinant to write down basically a formula for the inverse of a matrix. You remember last time we can actually compute the inverse of a matrix by doing row reductions, but in the next video, we're going to show you that this is not very ideal sometimes for some type of matrices. And the new methods, which is called the adjoint methods, which utilize a lot of the concept of determinant, will be slightly more useful in that particular context. And we'll look at how we derive that formulas. And you should be able to understand the derivation as well. So you are not just take the formula and just use it. But in this course, we really do want you to understand how all those formula works. This is, again, a 300 level linear algebra at a college level. So we are not just telling you that's the formula and use it and that's it. No, you actually have to be able to explain why that formula works. So we're going to look at it in the next video. And also we have another methods to solve system of linear equations. And again, to utilize it, the concept of determinant again. They have some limitation as well. We'll talk more about that in the next video, but at least we have another methods that we can use to solve a system of linear equations, and that method is called Cramer's rule. Okay, so I will see you in the next video.